Let's examine one of each type instruction.
Firstly, we wrote the first instruction off the ROM, which will branch off to all these buses that you see here. Bits 31 through 36 are known as the opcode. The opcode is fed into the control unit where it's decoded and interpreted, and the data determines the operation that the process is going to execute in that instruction and sets up the paths here needed to do so. Now, because this is an R-type function, specifically add, which utilizes three registers, we're going to need basically two sources and one destination register. Reg DST in the control unit is set to high, which feeds into a multiplexer here and sets it to B, which will be our destination register later on in the program. Reg write is also set to high, signaling to the register file that the instruction being executed has resulting data that will need to be stored inside of the register file. Next, because this is an R-type instruction again, meaning that there's some type of ALU operation to perform, the ALU controls for second bit, like the middle bit, is set to high, which tells the ALU here that the operation will be arithmetic and not Boolean. Bits 5 through 0 are also fed through a bus through to the control unit and basically determine what specific type of arithmetic operation will be performed, in this case addition, and the resulting value is also passed through to the first and third bit of the ALU control line fed into the mod ALU, which is basically the ALU telling it that it's going to do addition. Now, ALU source or ALU SRC is set to low simply to tell the multiplexer which data will be utilized in the operation. So if we trace that, that feeds into here, basically telling it that it's going to take in the A bus here, and this is also going to take in the A bus here. So basically, the ALU will be performing the addition on the initial values coming in through here. Jump and branch are both set to low because neither of these functions have any role in this instruction, so they can be ignored. Additionally, memread, memtoread, memread, memtoreg, memwrite are also set to low because there's no instance of random access memory manipulation in this instruction. Bits 25 through 21 indicate which register's data will be read from and passed on as the first argument into the ALU, and bits 20 through 16 are the second argument into the ALU, and these pass into the ALU where they are calculated, and the result is then carried here, and because there's no data manipulation here, it just skips the RAM completely and goes straight to this multiplexer. And because reg write was also set to high, the result is then carried back into the register here where it is stored. Bits 15 through 11 indicate which register will store the results of the calculation, and if you recall, reg DST here opened up a pathway via the multiplexer, this one, for that data to be passed through to the register file. So that is saved here in the register. Lastly, then to get the next instruction of the program, we add 4 to the current address here in this constant value, and the updated address is then loaded into the program counter as the next instruction.
For the I-type, we're going to be looking at the store word function. The opcode, which comes from the 31st to 26 bit, is decoded by the control unit to activate the components required by store word. Part of the instructions for store word is to add an offset to the memory address stored in a register. Hence, the ALU control, which is here, will be a high to allow for the utilization of the ALU. Since we are storing something, we know that the memory will be rewritten, and hence, memwrite, which is here, will also be sent a high signal. And ALU source is also a high input to toggle the second ALU input, where it goes into the multiplex, where it activates the second, where it toggles the multiplexer and allows for B to go through. No other components are used, and hence the remaining lines are low signals. Bits 25 to 21 of the instruction is the register that contains the destination address where the data will be stored. This gets read and is passed into the ALU. It goes into the ALU immediately after. Bits 20 to 16, which is here, indicates the register that contains the data that needs to be written to memory. This is a read, this is read, and is the input of the write data input of the memory unit. So it goes here. And it goes into the write data of the RAM. The remaining 16 bits, which is the offset, which is here, is extended to 32 bits using a sign extend. Where in the sign extend, it takes the 16th bit of the remaining 16 bits and replicates that single bit for the bit 17 through to the 32nd bit. And since ALU source is toggled, since ALU source toggled the multiplexer, the offset is the other input of the ALU. And since this is toggled, it takes B and goes in. The ALU will then add the destination address with the offset, and the result will be used as the address that tells the memory unit the location with which to store the data. And since the memwrite line is high, it enables us to write data because it goes into the write enable of the RAM. And since we have the address where data is supposed to be stored and we have set data, the path for store word is now complete. And the program counter will pass through the carry look ahead adder and increment it by 4 so that we can get the next instruction.
First, we load the instruction from the ROM, and this address splits off to all these buses like before. And it's much like the instruction types before. The opcode is fed into the control unit where it is decoded and interpreted. Firstly, in that control unit, branch is set to high, which feeds into this AND gate that you see here. ALU controls second bit, so the middle bit is set to high because there will be an arithmetic operation to execute, specifically in this case, a conditional check. So the middle decimal of that, bits 5 to 0 are simultaneously fed into the control unit and determine what type of operation is going to be performed. And the resulting value of the combinational logic is passed again through the ALU control as the first and third bit of the ALU control line feeding into the ALU. All the other signals here are set to low, meaning that they're not going to be used. Bits 25 through 21 again are the first register, and this is the second register being passed into the ALU. And in the ALU, the conditional check is executed, and this is done by subtracting the data in the second register from the data in the first register and testing to see if the result is 0 or not. If so, the ALU sends a high from here to check if it's all a 0. It sends a high to this AND gate, making it pass that AND gate. If not, the address and the program counter would simply be incremented by 4 and continue in its regular order without utilizing the rest of the instruction. However, for this, we're going to assume that it does pass. After passing the AND gates here, the processor now needs to be loaded with the jump address carried through bits 15 through 0, which, if we trace back to here, is in the initial instruction code. However, because we only have 16 bits, we have to sign extend and then that to 32 bits and then left shift it to convert it to bytes, and that's exactly what we want. Also, this address is then added to, through this 32-bit CLA here, this is added to the incremented address that we see here after we add 4 to it here, the incremented address of the current instruction loading the processor, so that's going to follow all the way to here, to this. These are going to be added together in order to load the processor with the new instruction.
Now we'll be looking at the J-type instructions, which is also the jump function. The 6 most significant bits, bits 31 through 26, is taken from the instructions and into the opcode. Every other function in the control unit is on low, except for the jump. Jump is on high signal, and when jump is on high signal, it toggles the multiplexer here. The read address has to be 32 bits in length, but there's only 26 bits remaining in the instructions. The remaining 26 bits from the instructions is then passed into a left shift, where the two least significant bits will be 0, and the remaining 26 bits will be left shifted by 4, which is also a multiplication by 2. So the two least significant bits will be 0. The address from before will have its 4 most significant bits truncated, and this will be reused later. Using the 4 bits from the address, we append it as the 4 most significant bits to the 28 of the 28 bits. So here, it increments the address by 4. We take the 4 most significant bits here and add it to the 28 bits. This thus giving us a 32-bit. So the component that we will be looking at in detail is the ALU. In particular, we will be looking at one binary operation and one arithmetic operation.
We'll be looking at the ALU when the function code is 001. When f is 001, it is an OR function. So when f is 001, the most significant bit is 0, so it selects A here. Next, the next significant bit is 0, so it selects A here and here. And when the least significant bit is 1, it selects B here. So let's go through that process. Here, it takes in A, so it takes in input B and goes through. And since the second significant bit here is 0, it takes in A, so we look at the A operations here. And since it takes B here, we just follow through and we look at this line. So B goes into the OR gate alongside the A input. So the output will be A or B. And since the multiplexer select A here and a B here, the output will be A or B. Hence the function OR. Next is when the function is 0, 1, 0, which is an addition function. When f2 is 0, it selects A. f1 is 1, it selects B and B here. And f0 is 0, it selects A. So it will select this multiplexer. So let's go through that process. It takes in input B and it goes into the CLA alongside the A input. In the CLA, B is added to A.
In particular, the CLA is more efficient than a ripple carry adder because it calculates the carry bits before the sum bits, while the ripple carry calculates the carry bits alongside the sum bits, so it is in a way more efficient.
So the output of the addition between A and B is outputted here, goes into the multiplexer input B, and since f1 is 1, we take input B, output it here, f0 is 0, take A, and the output is A plus B.
Here's the simulation of the ALU. When it's 0, 0, 0, the function is an AND, so it's A and B. When A is 0 and B is 0, it outputs a 0. When A is 0, B is 1, it outputs a 0. As long as there's a 0, it'll output a 0. It'll only output 1 when both A and B are 1. The next one is an OR. 0, 0, 1 is an OR. When if A or B is a 1, it'll output a 1. If both A and B is 0, it'll output a 0. The next one that we're going to be looking at is when the function code is 100. When the function code is 100, the function is A and not B. So when A is 0, B is 0, B is not B is 1, it'll output a 0. It'll only output a 1 when B is 0 and A is 1. Because not B is 1 and A 1 and 1 will output. When the function code is 101, it's A or not B. So for it to display a 0, B has to be a 1. A has to be a 0, because not B will be a 0, and A or B, when both are 0, will display a 0. Everything else is a 1, so it's here. Next, we'll be looking at the arithmetic operations of the ALU. 010 is the addition function. So let's change this to sign decimal. When A is 7 and B is 8, 010 and 010 is an addition. 7 plus 8 will result in a 15. 7 plus negative 50 will result in a negative 43. And when the function code is 110, it's a A minus B. 7 minus 8 will result in a negative 1. And 7 minus 50 minus negative 50 will result in a 57. And when the function code is 111, it is the SLT function, which is the set less than function. It'll compare A and B, and if A is less than B, it will have an output. So it'll have a negative output. So since 7 is less than 8, it'll have a negative output here, but 7 is not less than negative 50, so the output here will be a 0.
When we examine the first, say, 4 square numbers, there's an apparent pattern that emerges. So the square of 1 is 1. So we'll refer to this as our base case. The square of 2 is 4, which is 1 plus 3. The square of 3 is 9, which is 4 plus 5. And the square of 4 is 16. It's 9 plus 7. So as we can see here, basically the distribution of the square is basically the previous square plus 3. And then here we have plus the previous square plus 5, which is actually just 3 plus 2. And then here we have the previous square again, which is 7 plus 7, which is 3 plus 2 plus 2. So from here we can see that for every step n after 2 squared, we just take the previous square and add 3 and then add 2n. So if that was a formula, that would be previous square plus 3 plus 2n for any number after the square of 2. Now, because we start from 1 and build up from there, for any number after 1, we will always have the result of the previous square. So this is always given. So all that's left for us to do is calculate and add the 2's. How many 2's, basically? Stop. So in our initialization function, first we define the initial increment value of 3 that we saw on the paper. And we store that to register T2. And in register T1, we have the value of 1, which is our base case, which we defined as our base case. So generally speaking, in our code, register T1 is always the output, so it's the squared value. And register T2 holds the value of the 3 that we increment plus the n number of 2's that we add to that output later on. So if we move to the loop here, first we store words, so we output our squared value, which in this case is 1, which is in register T1, and then we add the previous square, T1, we add the previous square, T1, plus the value 3, that our initial increment, and store that in register T1, and that makes this a 4. And in register T2, we add 2, which is going to be our future increment. So in the next loop, we're going to add that to the register. Now, if we go back here, this is a loop, and it loops back to the beginning of the loop. So that basically store word outputs 4 now, which is in T1, and then it adds the previous output, the previous square, which is 4, plus T2, which is now 3 plus 2 from the previous run, so 4 plus 5 is going to give us a 9, so that's going to be the output of our next iteration, and then we add 2 more to T2, so that basically keeps looping around until reset.